Welcome to today's session. So today we are going to look at the two-way Anova, and we are also going to look at chi-square test of independence or chi-square test of association. So in the previous class, we looked at one-way Anova. So today we are looking at two-way Anova. Anova, we said it stands for analysis of variance. Analysis of variance. So let me start by sharing my screen. I think it will be a good thing for me to do that. Yeah. So we have data sets that we're going to use here. We already shared them in the learning management system, so you can be able to check your email or your learning management system. You should see an update about some of these things that I'm going to use here today. So two-way Anova. So it's used to determine whether or not there is statistically significant difference between the means of three or more independent groups that have been split on two factors. So the purpose of a two-way Anova is to determine how two factors impact a response variable and to determine whether or not there is an interaction between the two factors on the response variable. So we are going to break that with an example. We are going to break it down with an example, with the use of an example. So for example, let me say that we have something like, okay, I think we'll just use the example that is here so that it can be easier for us even to run and analyze. So a case study that we have here is, let me run this. So a case study we have here, a researcher wants to know whether or not plant growth is influenced by sunlight exposure and watering in frequency. Let's say just a farmer wants to know whether the plant growth is influenced by sunlight exposure and watering frequency. Now here we should ask ourselves, how is the farmer going to measure the plant growth? What is the measurement in plant growth that the farmer is going to use? Okay, so she plants 30 seedlings, that's 30 seeds, and lets them grow for 2 months under different conditions for sunlight exposure. You see, now we are going in depth under different conditions for sunlight exposure and watering frequency. After 2 months, she records the height of each plant in inches. So that means that we have another variable known as height, so which is now being recorded as the plant growth. So that is the variable we call a response. Now we want to find out sunlight exposure, how sunlight exposure and watering frequency influence or impact height of a plant in the data set that we have. So we start by importing the data. Of course, we have to define the library, the packages we're going to use. So in this case, first of all, to read the data, we are going to use the pandas as PD. So we import pandas as PD. And then from there now, we reference our data set. So our data set is called session data. It's called session data, yeah. So I think in the learning management system, it has also the same name. It's a text file. So you import it as a CSV. So CSV is just a comma separated data. It's a comma separated data. So it's a text file. You can check the text file here. The extension is txt. That means it's a text file, but we are importing it as a comma delimited. So it's a CSV file. So we read it as the way we usually read the other data. And then from there, we view the head just to have an overview of how our data looks like. Let me just first of all run the pandas library and then run the data. Yeah, so I have imported the data and then now I run the head. So I don't know if you already have the data set.
The one you sent is smoking data.
Oh, smoking data. That is for the chi-square test. There's no session data.
There's no session
Yes.
data.
there's no session data. Let me just check. Okay, let me just check. Let me stop sharing and then check it out. Okay, just check. Python. Okay. Uh-huh. Anova dataset that was posted yesterday, the other day on Monday, and then Chisquare. Okay. So let me just post it there under Anova so that we can be able to access it from our end. Let me call it two-way on top, two-way Anova. Yeah. Then we are assigning it. So we said it's a text file, so you will use CSV to import it. So I have just posted it, so you can just check your emails, and then you can go to your learning management system. So once you have it, I want to know, I want to see, someone should share your screen so that you can perform some simple view about the data so that we can know how data is. And then from there is when now we can be able to conduct the two-way ANOVA. So once you download the data, let us know so that we can be able to help us import the data. Are we there?
Yes, we are trying to download.
Okay.
I don't think we have the permission to download.
Mm. What is it showing you?
Under download permission,
Yes, yes.
indicating viewers can download, but there's no link to download.
Can you click on it?
I've
Yeah.
just opened it.
Yes, yes. But you can see the data inside?
Yes, I can see the data.
Oh, okay. Godfrey, how about your site?
I opened
Godfrey.
it. Can you hear me?
Yes, yes.
I've opened via Google Docs and then downloaded it as plain text.
Oh, as plain text. I think I don't know. Let me just share with you via email if that is the case, so that it can be easier. Let me share with you via email so that it can be easier for you to download dataset. Yeah. So I have just shared, so you can download directly as a text from the email. And then now you can maybe Godfrey, you can lead us in two-way Anova, and then George will lead us in Chi-Square. So we'll be guiding you step by step so that we can be able to get it in depth.
Okay, I share my screen.
Yeah, you can share your screen once you download it. Okay, we can see your screen. Yeah, so yeah, you've just viewed the first 5 rows of the data. So this data is about, of course, how we were told that this data is about a researcher with 30 observations. So wants to find out uh, 30 plants and wants to find out if actually sunlight exposure and watering frequency affects the growth of the plant in terms of measuring their height. So we want to find out, we have 3 variables in our data, 3 columns. The first column is water, the second column is sun, the third column is height. So we just want to know which element does water contain into it using the data exploratory analysis. So we are going to check to do the value counts for each column for water. So we will call our data. So use data. You open the square brackets. Data, open the square brackets. We call water. Call water into the quotes. And then water dot value counts outside the square. Value counts, value underscore counts. Then you close the parentheses. Yeah, those ones. Then now we can be able to find out how many so we see how many variables do we have in our data. You can see we have how many groups. We have 2 groups. That's daily and weekly. So each has 15 records. So we can also do the same for the sun. For us also to know the sun intensity, just go to a new copy and go to the new cell, and you can also change that to sun, and we can also be able to check the value counts for sun. So we see that from there our data has 10 for low, 10 for medium, and high sunlight intensity is 10 as well. So from there we have just done some exploratory. Now we at least understand how our data looks like. Maybe if we just want to check if we have missing values in our data, maybe we can just do the .info, df.info. So for this case, we will just call data.info because that's how we defined our data. We close the parentheses and we run it to check if we have any missing observations. So we see we have each variable has 30 observations and there is no missing values. We have 2 objects and 1 integer, the data types. So at least from here we can know that water is categorical, sun is categorical, and height is an integer. So from there, now we can now perform a two-way Anova, two-way analysis of variance. So what I will do to save time, because Godfrey is the one who is typing, so I'll just the analysis in the chat section, so you can take it and paste it in the in your cell so that you can interpret it. Yeah. So Once we are there, Godfrey, are we, George, are we together? George, are we together so
Yes,
far?
we are. Yes, we are.
Okay, okay. So once we have seen how our data looks like, now we want to perform two-way analysis of variance. So what is it important? What is it important to know in the analysis of variance? In the analysis of variance, we are required to know the null hypothesis. That's why we learned about hypothesis testing before going to the analysis of variance. We must know the null hypothesis and the alternative hypothesis. So for in this case, you will have like three hypotheses to test. The first hypothesis is that you'll be testing if water has an influence on height, like watering frequency. If watering frequency has an effect on the height of the plant, that's the first hypothesis that you should test. So it will have, it is null and it is alternative. So the null hypothesis is that a water does not have an impact on the plant height. Watering frequency does not have an impact, does not have an influence. There does not have an association on the plant height. And then the alternative hypothesis in that case will be that there is an influence. There is an influence. There is an influence of watering frequency on the plant's height. Then the second hypothesis will be testing if sunlight exposure has an influence on the height of the plant. So in this case, we will be trying to see if low, medium, height, different levels of sunlight affect the plant height. So for us to do that, we set hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis will be that sunlight exposure does not have any influence on the height of the plant. That means that whenever you put a plant in a low sunlight intensity, whenever you put plant in medium sunlight intensity, whenever you put the plant in high light intensity, all will grow with no effect, being that they're just in the sun intensity. That's what we are going to test. The third hypothesis is that there is no interaction between water and sunlight on height. Like the combination of water and sunlight does not have an influence on the height, on the plant's growth. So we are going to test that. The last one is that there is no interaction. There is no interaction effect between the two categorical variables on the response variable. So there we also, of course, we have to set the hypothesis, which is now there is no and there is. So there is no is the null hypothesis and there is the alternative hypothesis. So far now, do we understand maybe what we are doing? And then from there, we can explain the code. Are we now together with the two-way analysis in this example? So far? Have we understood it? If you can hear me.
Yes, yes.
Okay, okay. Thank you. So we proceed to the interpretation. So first of all, we start with the importation. We import stats model.api as SM, where we can be able to get the OLS, the ordinary least square method that we will see. So we will get it from the SM, of course, from the stats model, and as well it is also there in the from the stats model dot formula. We are now from dot API. We are also importing the OLS. Of course, that is just the essence. So from the SM, we will also be able to get the stats dot Anova LM. Linear model. LM is linear model. So Anova linear model. So we can be able to get the analysis of variance model, and then we will be able to print the table. So we start by creating a variable, define the model. So we start by creating a variable known as model. Then we say equal to Then OLS, ordinary least square. From the ordinary least square, we are creating a model. We're creating a model, height, which is the response variable. We create it on the categorical variable. So here we are using C function to specify that water is a categorical variable and C is sun is also a categorical variable. So we are using C function for us to be able to specify that these actually they are categorical variables in Python. Suppose they were numbers, we could have specified that they are categorical variables using the same. So Python will know that these are categorical variables. And then from there, we refer to our data sets. So Godfrey, you'll have to change that df. For mine, I had used df. You should change it to your data. Yeah. So the first data is just the first name data is the name we are calling a parameter or an argument in the OLS model to assign it the data set that we have. So for Godfrey's case is data, the name of the data set from the way he imported it. So it will be data is equal to data. Then dot fit, so we call a method known as dot fit that will help us to fit the model. Then we perform the two-way ANOVA. Perform the two-way ANOVA by now creating another variable known as ANOVA table, of which it will enable us to create a table, is equal to sm.stats.ANOVA, our linear model. Then we call the model we have created in the previous by defining the model. We call that model, and then we specify the type of ANOVA under type. So we specify that it's a two-way ANOVA as an argument in the ANOVA LM model. Then now we can be able to run our analysis to find out what do we get. So from there, we are presented with the ANOVA table. That's what we call the ANOVA table for the two-way analysis of variance. So in this case, that's why we were testing 3 hypotheses. That's why you see we have P, where we have the probability value, the probability values, or the F values also hit there. The 3 cases. The first one is for water, the second one is for the sun, and the third one is for the interaction between water and sun intensities and the watering frequency. So we start with the first one. The first one is we start with the water categorical variable known as watering frequency, and we have the sum of squares. The sum of squares is 8.53333. So that is just mathematical sum of squares of the mean for the groups. There's a theoretical way of computation. We are not going into that. The degree of freedom, the DF is 1. Of course, in water we had two groups. We had male and female. So to get the degree of freedom of water is n minus 1. The number of groups that you have minus 1. So that's why you see there 1. Then you go to the F statistic. F statistic is the theoretical computation that we get after performing some background mathematics to get the value that we can be able to test with a particular value from the table, F table. There's an F table in the theoretical computation. But now we are usually provided with the p-value. The p-value that help us not to refer to the F table. We usually compare this F statistic with the F table, and the interpretation is usually different from the p-value. How we usually interpret p-value is the opposite how we interpret the F value. So for the F value, we say if it's greater than the critical value from the table is when we reject. But you see for the p-value, we reject if it is less than. I think that's the difference that you can be able to note there. So we are using the p-values here because we don't reference to the for the table. We cannot work with F tables everywhere. We usually reference to our confidence level, the significance level of 0.05. So we check the p-value there that is associated to the F statistic, which is 0.0005 0.27, the first one for water. So that value is less than 0.05, which leads to the rejection of the null hypothesis. So what is the null hypothesis? The null hypothesis was that water has no influence on the height of the plant. Watering frequency has no influence on the height of the plant. So when we reject that, that means that the alternative will be that the watering frequency has influence on the height of the plant. That's the plant growth. That is the first case that we do. So that means that watering daily and watering weekly has an impact on the plant growth. Has an impact on the plant growth. So let's also check sunlight intensity, sunlight exposure. The second one. The second one, we have its sum of squares, we have its degree of freedom. Remember, sun has 3 categories: low, medium, and high. So to get the degree of freedom, you take n minus 1, which was 3 minus 1, you get 2. And the F statistic that is associated to this sun is 23.3125. So while reporting, you have to report the degree of freedom, at what degree of freedom, and the F statistic value. This will help the person who will be referring to the table as well. When we refer to the table, we usually use the DF, like the 2 for the sun, and the residual DF, which is 24. Which is 24 for the overall data that we had. So in this case, we are going to do the interpretation based on the p-value. Our p-value is 0.000002. This value is also less than 0.005. 0.05, sorry. So since it is less than 0.05, we also reject the null hypothesis. What was the null hypothesis? The null hypothesis was that the sunlight exposure has no influence, has no effect on the plant growth, on the height. So when we reject that, that means that there is an influence, there is an effect of sunlight intensity or exposure on the plant's growth. The last part is the interaction between water and sun. So that we have an interaction effect of water and sunlight intensity on the plant's growth. So there, according to its probability value, there is no significant interaction effect between sunlight exposure and watering frequency. Like there is no at a point where when we frequently water and we have high intensity, the plant is going to be I don't know, high or what. So there is no that interaction. That's what we mean there. So we are not yet done, because we have now to find out, because when you are doing research, you need now to tell us. Of course, you have just told us that the analysis of variance table has just told us that watering frequency has there is some difference. So which advice will you give to the farmer? If you are the researcher, you need to give the farmer an advice, because you'll just tell the farmer there is some, when you water daily and when you water weekly, there is an impact on your plant growth. You should tell the farmer, water daily. You have to water daily, you have to water weekly. You have to tell the farmer that. If it is sunlight intensity or sunlight exposure, you have to tell the farmer that you have to use either low intensity of light for your plant growth, or you have to allow medium or high. It has, which impact does it have on your plant growth? So after understanding this, we should go to the farmer with a solid solution. We are not yet done with reaching to that basis. So for us to reach to that basis, we compute something we call multiple comparison. like the one we had for one-way Anova. We do a multiple comparison. We do a multiple comparison. So I want us to perform that multiple comparison using Turkey's HSD, like the one we learned. So maybe I just take here some code that will help us to import and then perform Turkey's HSD and then interpret the Turkey's HSD, and then we can be able to visualize the results and be able to understand each even better in a visual way. So I'm sharing in the chat section the Turkey's HSD that is associated with our test. So in this case, we want us to test, check the chat section for the Turkey HSD. We want to test the sunlight intensity. So we just need to understand, for example, in the sunlight exposure, we need to tell the farmer, your plants require high light intensity or low light intensity. We need to know how is it different? How is it different? Okay. So from here we start by importing from the stats model.stats.multiple comparison. We are importing pairwise Turkey HSD. When you use the navigation tools like SPSS, you just see these things, you just check them and then add to your model. When you use things like Stata, you can be able to also use the command or just navigate and populate your results. Using Python, we have to import these methods from particular packages. So we import the pairwise Turkey HSD, and then from there, we create a variable known as Turkey, and then we say equal to, then we call a method which we imported, which is the pairwise Turkey HSD. And then now from the endog, we have an argument known as endog. We now reference to the data that we are going to use to do the response variable. So we reference to that data, we subset it, we assign it to the endog. Endog is the data that we have, the response data that we are going to use. And then from there, we specify the group. So the grouping variable, what is the grouping variable in our case? It is sun. For example, we want to look at the sunlight exposure. So we also reference that data to the sun. We reference that data to the grouping variable. And then from there, at what alpha, at what level of significance is the 0.05 that we usually reference to while making the interpretation. So we reference our Turkey HSD to the alpha of 0.05. You can still adjust your alpha to make your decision more precise. You can even change it to 0.001 as long as you'll be understanding. But the default one is the 95% level of confidence, which converts to 0.05. So when you run that, you get another table for the multi-comparison. You get a table for the multi-comparison. So this table compares the means for the high, low, high, medium, and low, high. In this case, we are just looking at the sunlight intensity exposure. That's sunlight exposure. So we see the mean differences there. We see the mean differences between the plants that were grown under high intensity and the plants that were grown under low intensity. The mean difference is negative 1.7. We look at the adjusted probability value, which is 0.001, 0011. And then we have the lower bound and the upper bound for the mean, the lower bound and the upper bound for the mean difference. That is the population. That is the upper. It gives us an estimate of the population data. That, like, maybe we just took a sample of 30. What about the remaining samples? So it is telling us in which range will the mean difference for the remaining samples for low and high will range. the remaining samples, the population data mean for the low and high will range between negative 2.741 and negative 0.659. That is the mean difference for the population data for for the sunlight intensity, which is high or low. And then now we look at the rejection and the failure of the rejection of the null hypothesis. In this case, it is true. It is telling us it is true. So that means that there exists a difference in the plants that were grown under high light intensity and low light intensity. That exists a difference. It is true we are rejecting the null hypothesis. The null hypothesis here is that there is no difference again between those plants that were grown under high light intensity and low light intensity. Now, under light intensity. So we are now here rejecting that. So we reject. And then if it is true, we take the alternative that there is a difference. There is a significant difference. Actually, you can just look at the p-value and you can be able to even use that to reject or fail to reject. So multi-comparison provides us with an additional column, which is known as reject, so that you can be able to easily reference to it. And then we have high, medium, high, medium. So those plants that were grown under high light intensity, we are checking and we against those plants that are grown under medium light intensity. Their mean difference is negative 2.1. Their p-value associated to that is 0.001. And the population mean interval difference is likely to range between negative 3.141 and negative 1.059. Remember, all these things you need to put in the report. When you are writing a word report, Microsoft Word report, you have to add these values that we are using to interpret and their associated associations, like the ranges of the population. Where is it likely to lie? The lower and the upper bounds. You have to add that in the report. And then you look at the rejection. Of course, we reject because even the p-value there is 0.0001, which is less than 0.05, or alpha. So we reject that. So that, what does that mean? That also means that the plants that were grown under high light intensity differ in terms of their height growth against those plants that were grown in the medium. And then we do low, medium. We check if there is a difference between those plants that were grown under low and medium in light intensity. So their associated mean difference is negative 0.4, and the p-value there is 0.6124, and the lower and the upper bound are as shown, and as well the rejection here is that we fail to reject the null hypothesis. Why? Those plants that were grown under low sunlight intensity and the medium sunlight intensity, their mean difference for the height does not differ as such. There is no significant difference. There is no significant difference. So up to that point, I want us to plot. Let me see what we can plot. The visualization of the interaction. So I want to visualize those things and see. So import Seaborn. I want you to import Seaborn. Just there, import Seaborn. I'm pasting a code that will be able to use to run Seaborn. So import Seaborn. And also import matplotlib as PLT, so that we can visualize those heights. Import matplotlib as PLT, and then run that cell PLT. Okay, now take the code that we've shared, so that you can be able to visualize those heights to see how different are they, to see how the visualization part. So you can even put this in your analysis when you are writing a report. SNS, that is Seaborn. And then then now you can run, just run that, just check your data, just check everything. Your data is data, okay, and the interaction there for the plot, sunlight intensity, everything is okay. You can just run that so that you can see The module matplotlib. Just check the matplotlib title. Matplotlib.plt. Matplotlib.plt. Matplotlib.pyplot, not plt. Matplotlib.pyplot. Yeah, run that again, and then run the code. Let's see. Run your code again. Matplotlib.pyplot. Yeah, so there we don't get any error. And when you see it, you see now here we can see the visualization of how these means differ. You can see the mean for the low. The mean for the plants that have low height is around 5, 4.9 something there. You see their color there. The sunlight medium, the medium sunlight, their mean is around 4.5 something, the yellow. And then the high light intensity plants have higher mean for the plant growth, which is almost 7. So you see, we can now visualize that. And after visualizing that, now we see that actually the plants that are grown under high light intensity are likely to grow faster compared to those plants that were grown under low light intensity and those plants that were grown under medium light intensity. And also, when we compare low, we compare high, medium, high, low, there is a difference. So that shows that those plants that were grown under high light intensity differ from those plants that were grown under low and medium. That's the interpretation we have had above. And then when you look at the low and medium, there is no that difference, even from the statistical view and also the visualization of view. There is no that big difference between the 4.5 something and the 4.9 something difference. So there is no that big difference between the means for those plants that are grown under low light intensity and high medium and medium light intensity. So having said that, I would like to give an assignment. An assignment is to perform analysis for water. Perform the analysis for water. Just like the one we have done for the low and medium height, you have to perform the analysis for the water categories so that we can be able to know how is it different daily and the weekly frequency. So that's an assignment that you'll be able to do at your time so that you can also identify that. Any question here? How is the interpretation? How is the visualization? And how is the power of two-way analysis of variance? Can I get some reactions on that?
Can you go back to the interpretation?
Okay. Just go to the interpretation, Godfrey.
Groups, Yeah, that
Yes.
the first one, yeah, that one.
Yes.
The last column. I didn't get
Yes.
interpretation on the last column.
The last column for the Anova table or the last column for the multiple comparison table?
For the ANOVA, the first one, the first table we
the Anova table. Yes, the last column is the p-values. The last column is the p-values that we are checking to reference to the 0.05. So if the p-value is there, the values that we see there, the probability value, pro is the probability value. So is the p-value. So that value, we check it. If it is less than 0.05, we reject the null hypothesis. The null hypothesis, remember, we set the null hypothesis for water, for sun, and even for the interaction between sun and the sun and water intensities. So maybe you can pause your question because we are using that to reject the null hypothesis in that table for ANOVA.
I just wanted to get the interpretation.
So the interpretation, in this case, for water, we are taking water impact on height. Water impact on height. So the null hypothesis is that watering frequency has no impact on height. plant growth. So the alternative is that watering frequency has an impact on plant growth. So when you look at the value 0.000527 is less than 0.05. So that means what? We reject the null hypothesis. And what was the null hypothesis? The null hypothesis was that watering frequency has no effect on the plant growth. So when we reject that, we take the alternative. So the alternative is that the watering frequency has an impact on the plant growth. The same way you interpret for the sunlight intensity. George, back to you.
That's okay.
Okay. Thank you. So you will practice the same for, yeah, you can just stop sharing. Okay, you have a question? Yes. Proceed, Godfrey.
Yes, you explained something about degrees of freedom and how to interpret, how the user will use the degrees of freedom to interpret this with the 24, the residual degrees of freedom. How does it work? What's the connection between those?
Yeah, so this one is usually used, especially while using the F table. When you do a search about the F table, you'll be able to get a particular table that has DF as a column and has some percentages of p-value ranges, the confidence interval ranges on your first row. The first column will be DF, which is the degree of freedom, like the values that are free, that can be varied. That's what we call as the degree of freedom. So we usually use these values that we see here while checking on the table to compare the F statistic value. But if we use the probability value, we don't use the degree of freedom in interpretation, but we usually include it in the interpretation. So we say that we rejected the null hypothesis at p-value 0.00527 with an F statistic 16.000 with a degree of freedom of 1, comma the 24 as 1, 24. So the degree of freedom, we usually put it into bracket 1, 24, because when you want to reference to F statistic and F critical, you'll need to have the two pairs for the degree of freedom. So that is the theoretical interpretation of that. When you want to use the F table in most of undergraduate level, for that, they usually use the F table. But once you are provided with the F statistic, you do not need the F table for you to interpret the results of your data. I don't know if I am clear there.
Yes, that's okay.
Yes. So we usually use just the DF to either reject or fail to reject the null hypothesis. So for example, I don't know if you can just see how the F table looks like. Maybe you can just Google, we usually need DF1 and DF2. So something like that. So maybe you can just Google, but you can later use that, but it will make your life more difficult. Better when you just use the the probability value, and later you can research on how you can use the F statistic if you are interested to know how to use it. But in this case, I suggest the utilization of the probability value in interpretation. But remember, in reporting, you have to include the F statistic, you have to include the degrees of freedom values in your interpretation while writing a report, the findings, and also the percentage, the confidence interval, the upper and the lower bounds. Some results usually populate the upper and the lower bounds. So you also need to ensure that that is catered for. So I think that is okay. So you can proceed. To chi-square, unless there is a question on analysis of variance two-way. So for the two-way, there is an assignment on watering frequency. So you need also to identify that pattern using the watering frequency. So we can proceed to the chi-square test of association. So in chi-square test of association, chi-square test of independence, sometimes chi-square, we have different types of chi-square. We have different types of chi-squares. There are a lot types. I think there are three. Yeah, there are three of them. There is a chi-square test of independence. There is chi-square test of goodness of fit. Chi-square test of goodness of fit. And then there is chi-square test of homogeneity. Chi-square test of goodness of fit is used to test for normality, if your data is following a particular distribution. Goodness of fit, if it follows a particular kind of distribution. Chi-square test of homogeneity is used to test for the constant of variance. And then now we have the chi-square test of independence, the one we are going to use, which is usually the chi-square test of association. So remember in the previous class, we talked about categorical variables. We said analysis of variance requires a response variable to be continuous. While if you have two categorical variables, one is the response, and maybe one is the response, and one is the predictor. Especially in the logistic regression, a binary logistic regression, which is a machine learning model. We usually see, for example, you want to check, maybe you want to predict, for example, a Titanic data. We have Titanic data that is public in Kaggle. So you can be able, maybe you want to know people who survived, the association between people who survived and their level of class. If they were first class, if they were third class, if they were second class. So if you want to test if there is any association between the level of class onboarding, the class they onboarded as first class, third class, or second class. So you want to check if the level of survival was based on that level of the class of where someone onboarded. You make use of chi-square test. You test the association between the categorical variables. Remember, in logistic regression, binary logistic regression, our response variable is usually categorical. I think we'll look at that next week when we'll be doing an introduction to machine learning. So we'll be looking to that case for binary logistic regression. So let's just concentrate on the chi-square test. So first of all, before we conduct the binary logistic regression, we usually need to know if actually the variables we are relating to our analysis, they're significant, if they are important, if they have an impact on the response. Now we usually conduct the chi-square test of independence to check if there is an association between the variable that we are including in the model and the response variable. So chi-square test of independence determines whether there is an association between categorical variables. This is the notes that I'm reading here, some summary notes, and whether the variable are independent or related. So it is an unparametric test. It does not have that it has to follow a particular assumptions. Non-parametric test, that means that it does not follow any particular assumptions. Like the regression analysis, like the Anova, that data must be normally distributed and stuff like that. So it is an unparametric test. That's what it means. So it is also known as the chi-square test of association. We have looked at that. So this test utilizes a contingency table to analyze the data. Remember, we were creating a contingency table in Excel. So that's how the chi-square test does. It is thing. A contingency table is also known as a cross tabulation. Like in SPSS, you can get it being called cross tabulation, is what we call the contingency table, or a two-way table. So it's an arrangement in which data is classified according to two categorical variables. So for example, the data for the Titanic, for example, those who survived, they are labeled as 0. Those who survived are labeled as 1. Those who are not survived, who did not survive, are labeled as 0. And then this side, first class, second class, third class. Now we start grouping people who survived and were in first class, who survived and were third class. Which number, like the total number of people, counts the frequencies of people who survived and they were in the first class, who survived and they were in the second class, who survived and were in the third class. And again, we look at who survived and who did not survive and were in the first class, how many in terms of frequencies. And then the categories for one variable appear in the rows, and the categories for the other variable appear in the column. Just the way I'm explaining, the way we were plotting in the Excel. So each variable must have 2 or more categories. That is usually a condition, that a variable must have 2 or more categories. And then each cell reflects to the total counts of cases. Of course, we have total cases for each cell, either row-wise or column-wise. That means you can get total for those people who survived, first class, second class, third class, total. You can get the total of people who were in first class, the column-wise. For example, if it's column-wise, first class, we are going to look at that. Let me don't even struggle. We have another example here, but I'm just referring to the binary logistic regression. So test of independence only assesses the association between categorical variables and cannot provide any inference about causation. Causation is very important. If you are conducting correlation, causation, that means direct influence. Causation means direct impact. Direct impact. Causation means direct impact. Association means correlation, having an association, having a relationship. So having a relationship doesn't mean that has a direct impact. For example, when we consider, let's say, I have this an example. Maybe we have high death rates from people who are dying in the swimming pools, in the beaches. And then we have high sales in the ice cream. And then we have a summer season. Summer season. Maybe we are using temperatures to measure that. So when we want, for example, can we say that death rates are as a result of high sales in the ice cream? Remember, when we try to see the temperatures or the sales, the temperature is not in the equation. Temperature is not in the equation. We just have high sales in ice cream and we have high death rates. Remember, these are 2 variables. We can check the relationship between the variables, and we will see that maybe there is a strong relationship. So relationship does not mean causation. So causation is where we have direct influence, direct impact. Actually, ice cream has no direct impact on the death rates. What has a direct impact on the death rates is the temperature. Because when it is high summer, we expect people to go out to beaches and stuff like that. The same way, we look at ice cream. When we have high temperatures, we may have a lot of people buying the ice cream. So you can see, actually, the problem that is in the equation is not in the equation. Something that is in the equation that is causing causation is the temperature, and not the swimming or the ice cream. So that's how we interpret causation. Causation is something having a direct influence. Hope now we understand causation and correlation. Correlation is just association, relationship, while causation is a direct influence. So chi-square does not show causation. It only shows correlation. So your data must meet the following requirement. Your data must be categorical. Of course, your data must have, in itself, being categorical, it must have at least more than 1 category. For example, if it is gender, you cannot have all female in your data. You must have at least male and female. You must have more than 2 or more. Yes. And then, and independence of observation. Independence of observation, that's very important. Just that the having that a person, this person is in first class and has died does not mean that the second person that's coming is also going to die because he's from first class. Yeah, something like that. Like there's in some independence of observation. And then there is no relationship between the subjects in each group. There is no relationship between the subject. The one that I've just explained, that is what the independence is. There is no relationship between the subjects in each group. That is what the independence is. And then the categorical variables are not paired. So we cannot use categorical variables that are paired. In this case, for example, the pre-test and the post-test observations. Remember this one, we use paired t-test to test such cases. And relatively, you need a large sample size for you to be able to interpret your data. Some of the things here you can still go through because you'll have this material just to know what are some of the requirements. So we go to the hypothesis, we set hypothesis about the chi-square test, and chi-square test has also null and alternative hypothesis. The null hypothesis is that the two variables are independent. Variable 1 is independent from variable 2. The alternative is that they are not independent. Not independent, that means that they have association. So the null hypothesis is that there is no association between the two variables. For example, the case we had for maybe Titanic, so there is no association between those people who survived and their level of class, their class level. That is the null hypothesis. The null hypothesis is that there is no association. The alternative is that there is an association. No, an association, the presence of an association is just the same as saying there is no independence. So it means they are dependent, they depend on each other. Yeah, so from there, we can go to importing the data. Of course, for me, you already imported pandas. So for you, you have to download the smoking data, and we want to use that data to learn chi-square test. And maybe Godfrey, George, you can take us through chi-square by first of all downloading the smoking data from Excel, and you share your screen so that we can use that to learn about chi-square test of independence. Maybe unless there is a question, but I think it is quite clear before we look at the data. So I'll stop sharing so that Godfrey, you can show us, not Godfrey, George, you can show us that because all your names start with G. So yeah, okay. So maybe do we have now a genesis of chi-square? Do we now understand the genesis of chi-square? Up to that, before we look to into the details. Do we understand the genesis of chi-square? Godfrey, is all right? Is everything all right on chi-square before we?
Yes. So,
Oh,
chi-square, yeah, okay.
okay. So we start by importing we import pandas as PD, and we from there import the data. We are calling it DF, and then we read it as an Excel file, looking at its extension. And then from there now, we view some first 5 rows of the data. And from there, we can see we have gender and we have smoking. So we need to see if gender and smoking habit, if there is an association, okay, based on this data, not based on the general assumption. We cannot generalize anything here because this is just data we are using to learn, and it's just generic data. So it has no anything personal with any gender. So we can proceed. So we have viewed some few observations about the data. So maybe we can just check to see which variables do we have, which groups do we have in each variable. So we can just do the DF, and then now we use the square. We use the square parentheses, remove the dot, we use the spare parentheses into the quotes to call gender, to see how many variables, how many groups do we have under gender. Outside call the dot value counts, dot value underscore counts, for us to see how many do we have for gender, for each gender. Close the parentheses, the curly brackets. Yeah, and then now we can run that to check. Yeah, so we see female, we have 209, male, we have 193 in our data. And maybe let's check the smoking. So just do the same for smoking variable. Do the same for the smoking variable. Do the same for the smoking variable. And then, yeah, we can see that non-smokers, there are 304, current smoker is 70, past smoker is 37. So that's the data that we have here. And maybe we just wanted to check if there is an association between gender and the smoking categories. So what we do is, so let's start by maybe importing some packages. So just to save time, I'll just paste this code in the chat section so that we can interpret it step by step. So there we go. I have the comments as well, so we can be able to know step by step. So you can just copy the whole thing, and then we will break everything into its own cells.
Where is the beginning? Here.
From SkyPy.
Or from SkyPy.
Yeah, from SkyPy.stats, import Chisquare. Yeah, from there down below. Yeah. So I want you to so I want you to copy the first part, which is from SkyPy. Yeah, the first part. Yeah, cut that, and paste in a new cell above. New cell above. Just click inside your cell. You cannot see. Okay, you cannot see the options for you to add. Okay, you can just add a new. Yeah, just add a new. Yeah, you can
Above.
drag. Yeah, you can just drag it up. Just drag it. No, hold it on the in ln. Yeah, just about yeah, there. Now hold. If you're using a laptop, you can hold on left click, and then you drag it up. Yours is not dragging.
It's not dragging.
Okay, just
Not
proceed. Or if you have another option, yeah, okay, yeah, okay. So paste that. So we start by running the first part. So the first part is from SkyPy.stats. We import chi-square contingency, for us to get the contingency table, and then we create the contingency table. So contingency table, we give a variable contingency table is equal to pd.crosstab. Of course, contingency table, the one we are importing, we are going to use it in the second part. But in this case, we are just using the cross tabulation method from pandas. So we are doing cross tabulation between two variables. The first variable is the gender, and the second variable is the smoking from the data set df. So we have to specify those columns. And then now from there, we print the variable known as the contingency table. Of course, we are going to leave space. We print contingency table as a title, and then we leave a line. We print the table down below the line. So you can just run that code so that we see how it is. You can control, you can shift enter while inside the cell you want to run. Yeah, for it to run easily. Yeah, so we have the contingency table there. So we can see that we have the smoking. You see now we have here the contingency table. We have the smoking as the first row, of which it is in column. We call that column, and then we call gender row. We call variable gender row, and we call smoking column. So we see we have numbers there. We have how many female are currently smoker, how many female are currently non-smoker, and how many female are past smokers. We can see how many male smoker, how many male are non-smoker, and how many male are past smokers. So from there, we can be able to now perform the chi-square test of independence to check if there is an association between the gender and the smoking habit. So for us to do that, we just want to assign values from the chi-square contingency method. Yeah, that's what we are calling from the table that we are going to get. Of course, chi-square contingency table is a method that chi-square contingency is a table, is a method that is a function from SciPy that we can be able to use contingency table variable, which is the contingency table above, to populate the chi-square value. That's the chi-square statistic, the p-value, the degrees of freedom, and if we also need about something expected. So we can just delete expected if we don't want, because it will it's not a requirement. But you can just print the way it is. There's no problem. So just run it, because I think the other lower part is just the print, which you already have. Expected and intended block. I think there is an indentation. Let me just check. Yeah, under the if stuff, there is some indentation there. Just let me just check. There is else. Did you leave else?
Let me check. Oh, you didn't paste.
Let me give you. There is else and there is a printable. Okay. There is else. So let me paste. So you only have the. Let me just paste the lower part from. Yeah. So if p is less than, if the p value will be less than the alpha, indentation there is the full color. So we are going to create. And there is a significant association between the gender and that. So first that, and then indent. Let me see else. Then so expected an indentation block. It's just indentation. The indentation is just here under if. Yeah. Okay. Yeah, there we go now. Okay. So what do we see? We just added the interpretation using the if and else statements, and the way we did in the previous classes. So I'm not able to talk a lot about.
You are far from the mic.
Oh, okay. Let me see. What about there? There? Okay. Thank you. So from here we can see the chi-square statistic value. The way we head for the F statistic. We also have chi-square table that we usually check. So we have the p-value here. The p-value here is 0.204, of which we compare it with 0.05, the alpha. to reject or fail to reject the null hypothesis. Remember, how did we say about the hypothesis? The null hypothesis is that the variables are independent. There is no association. Isn't it? What did we say about the null hypothesis? We said that the variables are independent. The gender and between gender and the smoking habit, they are independent. Independent meaning that there is no association. They are not associated. The alternative is that they are associated. So from here, the p-value is that we failed to reject the null hypothesis. We failed to reject the null hypothesis. That means that there is no significant association between gender and smoking habit. So we failed to reject the null hypothesis. Another table down there is just the expected values that are usually computed. So when computing chi-square, when you look at the theoretical computation of chi-square, we usually have the observed values and the expected values. So those are manual computations. So we usually not include them in the analysis. But what is important is the chi-square statistic value, the p-value, and the degree of freedom that is associated with the interpretation. I think it's easier from the way we started with the in-depth overview about chi-square, and up to here now we've been able to look at its interpretation. It is quite easier to interpret and run. So maybe I get feedback from you because this is the last part of our session today about chi-square.
From the interpretation, yeah?
Yes.
From these lines, eh?
Yes.
Alpha is 0.05, eh?
Yes.
So when probability
Yes.
is less than 0.05,
Yes.
that's when we say there is a significant association between smoking.
Yeah, we say that there is a significance. It's like we are building interpretation inside our code so that
Yes.
we don't struggle again looking at the p-value and looking at the alpha. So we include that interpretation in our code so that it can be easier. We just read the the output. So that's why we usually encourage also learning the if statements at the introduction part, the way we did. Yeah.
So our null hypothesis
Yes.
was that variable 1 and 2
yes, and variable 2 are independent.
are independent.
Mm.
Also meaning there is no association.
Yeah, there is no association between gender and smoking habits in this data that we have.
I get it.
Yeah, so just in case you have any data, because health data is very sensitive, so you must be very sure about the decision you're going to make about the sample data that you have. But in this case, this is just a generic data we are using to learn. It does not have any implication on human. Yes. Hope that is okay.
It's clear. It's clear now.
Okay. Thank you so much. So I'll be able to share in the learning management system a data set that you will be able to learn on how to perform chi-square tests. For the two-way Anova, the assignment we have is to run the water analysis about watering frequency to check the multi-comparison for that. So you can still be given any data, look the potential of using which kind of test. So that's why it's good for you to familiarize yourself with the different type of tests for it to be easier for you in terms of interpretation and which one do you need to use and how are you going to make a decision. Of course, you must start by looking at the data type you have for you to know which is the response, which is the independent, the predictor, and stuff like that. Predictor is just the independent. Response is the dependent. Yeah. So up to there, that marks the end of our session today. So